Welcome. My name is Joseph Lefew, and this is a presentation on control logic injection attacks on industrial control systems. This paper was originally presented by Hyunguk Yu and Irfan Ahmed. I apologize if my pronunciation of these names has been incorrect. So let us get started. So here we begin with our abstract review. A few key words to familiarize yourself with as we explore this paper are as follows. Control logic, which is a key part of software that controls the operation of a respective program. Code injection attack, which is the exploitation of a vulnerability in code via insertion of malicious code. Programmable logic controller, which is a programmable electronic device used in industrial automation to provide logic and sequencing controls for various types of machinery. Ladder logic, which is a style of programming used in programmable logic controllers. It consists of rungs of control logic that resemble those of a ladder. Critical infrastructure, which is any asset that is essential for functioning of society and economy, such as agriculture and food, emergency services, government, information and telecommunications, energy, transportation, banking and finance, post, and the likes. Remote control logic injection attacks are a major threat to industrial control systems. Stuxnet is a well-known malicious attack that affects a nuclear plant operation. We will discuss this in a bit more depth a little later in this presentation. However, this type of attack is not the focus. For the bulk of this paper, we will be discussing stealthy attack methods that avoid detection and manipulation of the firmware. These will namely be data execution attacks and fragmentation and noise padding attacks. This is the first paper to explore these types of attacks, and so hang on to your seats as we dive right in. Let's look at the introduction. As technology continues to develop at an ever-increasing rate, naturally systems become more and more connected, and PLCs are no exception. These systems are directly connected to physical processes. With this connection, they can manipulate the functionality at any given moment based off a predefined set of control logic. In industry, these PLCs help compile an industrial control system, or ICS. ICSs are continually being interconnected, often to business networks and even internet. With these increases in connectivity come increases in the cyber risk as well. Stuxnet became the golden standard of examples for remote attacks on ICSs. In this attack, a nuclear facility in Iran was remotely targeted via their Siemens S7 300 PLC. This attack was meant to sabotage operations and consisted of malicious code which was injected, causing oscillations in centrifuge motor speeds until system failure occurred. Since this attack came to light in 2010, more and more ICS bugs have been reported, and that number has increased almost exponentially year over year. So, in this paper, as an attempt to continue to revolutionize defense mechanisms for attacks, two new attacks will be explored. In the past, such as with Stuxnet, most attacks were not centered around remaining undiscovered. So, this paper was the first to explore avenues for stealthy transfer of malicious code. This is where we begin to look at data execution and fragmentation and noise padding attacks. These attacks will be demonstrated on two industrial-grade systems, Schneider's Electric Modicon M221 and Allen Bradley's Micrologix 1400. Using two very popular network intrusion detection methods, signature-based and deep packet inspection. Given that both methods fail to recognize attacks, it is imperative that more research is done to further the safety and security of ICSs. Diving further into these two new attacks, data execution disrupts the signatures that are based on packet header fields. It then downloads and inserts the compiled control logic to the data blocks of the PLC under attack. These data blocks are the communication mediums for all the input and output data associated with the process. Given that PLCs are not restricted on where code may be executed, the control flow is then able to be redirected to run these malicious code blocks. Looking next at fragmentation and noise padding, these attacks are the disruption of deep packet inspection, or DPI. Essentially, the packets are able to be broken into small enough sections coupled with noise, and then due to predefined address and offset header fields, this noise is removed, causing the code to be pieced back together and is now executable. Looking at the contributions, we can now jump into the finer details. First, I'll introduce the two attacks in more detail. Secondly, I'll present the successful attacks on both PLCs, which are from two different vendors, using their respective proprietary protocols. Then I'll present the results, evaluation, and finally discuss proposed next steps in research and solutions. As a little recap, PLCs are embedded devices, primarily closed-loop controllers of physical processes in real time. This loop is repeated in 3 defined steps. These steps are reading I/O from physical devices, executing that logic to reflect the gathered data, send results to the physical devices. Next, you have 4 types of blocks. These are configuration blocks, code blocks, data blocks, and information blocks. Configuration blocks hold the information about the other blocks. You can think of this like a nutrition information label. Code blocks are what contain the compiled code to be executed. Data blocks are what maintain the integrity of the variables utilized in the PLC. Information blocks are only used for project recovery by the PLC software. Existing control logic attacks are in 2 groups: traditional control logic attacks and firmware modification attacks. In traditional attacks, due to the lack of authentication, most attacks are done via man-in-the-middle style of attack. Stuxnet was a prime example of this. It was able to engage the software used for programming the PLC and then download the malicious code. 3 scenarios are presented in this style, referred to as denial of engineering operations, or DEO. DEO1 is the classic example, like referenced above, via download of malicious code. DEO2 is like this, however it involves uploading invalid code to crash the software as a whole. DEO3 does not require a man-in-the-middle position or to crash the controller, but it does prevent the file from being recovered. Firmware modification attacks, on the other hand, are not a typical attack approach in the real world due to the protection that usually prevent unauthorized firmware modification or only allow direct USB or SD card connection for changes. However, if this attack is made, it alters this firmware, which then prevents proper communication between the devices and hence makes it harder to detect with engineering software, as it does not actually alter the control logic. So now let's take a closer look at stealthy control logic injection attacks. First up, we have the data execution attack. Here you'll see signatures for detecting control logic attacks. Generally, a block transfer containing the malicious code must take place. In this, it is possible to prevent by not allowing transfer of block containing code over the network. Next, you'll see the vulnerabilities. 2 observations in communication protocols for PLC that make it vulnerable are: 1. Signatures cannot block the data blocks because they are required for proper execution of the code, namely to things such as HMIs. Second, you have PLCs which can have code executed at any place within them, therefore you could redirect execution to the malicious code. As can be seen to the right, at a high level, this is the key concept to a data execution attack. This is capable of evading signature detection for code blocks via the network. If we take a closer look into this, you'll see 2 distinct steps. First, you pick an appropriate random address outside of the code block range to avoid signature blocking, and then place that code logic code into that address. Second, once all the malicious code is in place, you redirect the pointer used to tell the PLC where to begin execution. You redirect this to the base address of the code that was just inserted. And voila! You now have a PLC functioning outside of the originally defined bounds. This is possible as a stealthy approach due to devices such as HMI which rely on data block with PLC, and hence these cannot be blocked with signatures. Next up in the stealthy control logic injection attacks, we begin to look at fragmentation and noise padding attacks. These are centered around avoiding detection by deep packet inspection techniques. Due to their proprietary nature, the semantics are usually unfamiliar area, and therefore it is best to avoid them altogether by making use of byte-level transmission of traffic. General approach is to gather a set of N bytes and use statistics or AI for detecting anything out of the ordinary. PLCs are vulnerable due to the inability of deep packet inspection techniques to detect relatively small-sized packets, so we can conclude the smaller the code, the less likely it is to be detected. DPI subversion via fragmentation and noise padding attacks are almost exactly how they sound. You would take the malicious code, break it into many fragments, 1 to 2 bytes for Modicon, for instance, append noise to the end of each fragmented section, and then each time you push another fragment, you address it such that it is put just behind the previous fragment and in front of the noise. Once you are finished, you're left with a full string of fragments making up the code, and then the noise will be removed at compile time and the code can be executed successfully. This is demonstrated in the figure to the right. It should be noted both signatures and DPI can be effectively avoided by using both attacks together, so transfer to a non-code block and a fragment such that size is 1 byte per noise blended packet. So let's look at implementation. In preparation of attack on Modicon, malicious code was developed and then the compiled code block was obtained. This was accomplished by monitoring packet transfer for normal operation, download, and then assembling logic code packets discovered by address fields of write request messages, as seen in figure 3 to the right. So now let's look at the main execution steps. There are 5 key steps. For step 1, gathering the information to determine where the address ranges were formed, so they investigated 2 configurations of the Modicon. These contain the start addresses and sizes of blocks, and once you know one, you can locate the next. For step 2, selecting an injection area is pretty straightforward. You look at address space layout and select an area outside of the code block. The authors discovered through reverse engineering that in the M221, the code block is always between the same address space. So this area just needs to be outside of the discovered static address range of E000 and FED4, and not in a configuration block, as these are not large enough for control logic. In step 3, you'll check the availability of the target injection area. You want to be sure you are not going to interrupt the operations of the PLC during cycle. If you choose something in the information block, this is not relevant, as that is only looked at during the use of the software. You have to be careful here not to brick or otherwise render the controller inoperable. So checking to be safe, you want to see an entire area filled with zeros, and this is available in the data blocks and what is deemed the unknown areas as discovered by the authors. Step 4 is where the transfer begins. By utilizing the prepared code from the preparation phase and inserting it into the target PLC. 1 byte of code plus 235 bytes of zero padding. These numbers are based on the max size of M221 protocol payloads being 236 bytes. Address of write messages will start at target address, aka address where the code is being inserted, determined in step 4. Lastly, the code pointer must be redirected to the malicious code, so on the next cycle, it is executed. Next, let's take a closer look at the implementation for an attack on a Micrologix 1400. This was a bit different as it uses the PCCC communication protocol, and the researchers could not find a way to execute non-code block code. So, I will only be able to discuss with you the results of the fragmentation and noise padding attack. To prepare for this attack, captured packets must be made into a PCAP file once they have been generated during that downloading process. Due to Micrologix requiring a complete and full sequence of communication, including all files for updating the logic, it is not as simple as just transferring the malicious code. So, the packets captured from the download are then going to be utilized. To execute this, the authors developed an attack tool. This tool uses the PCAP file from the preparation section as an input. It then prepares the code completely unmodified, except for the logic code, which is split into 2 byte pieces consisting of a code fragment and padding. This is demonstrated in the figure to the right. When manipulating these messages, one must change the size field to properly reflect the modified payload size, along with adjusting the needed offset in the sub-element number field to the total size of attacker code fragments to properly overwrite the inserted padding. Implementation of network intrusion detection systems was done for proof of concept. 2 tools were set up, one for signature-based representation and one for deep packet inspection. These are non-evading intrusion detection systems that are highly successful in detection of these traditional attacks. These will be used to gather data for comparison later. SCAPI-based signatures use packet header fields. SCAPI library from Python was used to create signature-based detection tools. In the Modicon M221, it was set to detect if write request was greater than address E000 and less than FED4, which would mean it contained logic code, due to the logic code always being within that static address range. Anagram-based deep packet inspection methods models one of the most effective payload-based anomaly detectors for ICS traffic without requiring semantic knowledge about packet payloads. This approach models a higher-order n-gram analysis. In this model, it is used to examine logic code instead of packets. They store all of these in a Bloom filter during the training phase. They determine the optimized size of n-grams for Modicon to be 4 gram and Micrologics to be 8 gram. They used 4 as the threshold amount for both PLCs, and if the amount of times these n-grams are in payload and the Bloom filter exceed this amount, then it will be flagged as containing logic. Settings for an experimental environment are as follows. They use the respective engineering software. So for the Modicon M221, you can see they used Machine Basic version 1.6, and for the Micrologics 1400, used RS Logix 500 version 9.05.01. An Ubuntu 16.04 virtual machine was used for attack testing, and a Windows 7 based machine was used for traditional attacker testing, such as for the man-in-the-middle attacks. So now, let us look at the different data sets that we're going to be used for evaluations. There's 3 main data sets: training data sets, traditional attack data sets, and attack data sets for data execution and noise padding. For the Modicon, 51 different programs were developed, 22 for training and 29 for attacking. For the Micrologics, 127 programs, 52 of which were for training and 75 for attacking. This has been illustrated in the figure to the right. These programs were made to control different critical infrastructures, and so no one program is alike. Training datasets were used to develop the Bloom filters. These were captured at download time and used as a basis for discovery. Again, these were discovered as 4 gram for Modicon and 8 gram for Micrologics. Looking at the traditional attack datasets, this is going to model a man-in-the-middle style attack, like discussed for Stuxnet and DEO attacks. So, to develop this dataset, they introduced an injection path utilizing engineering software with no evasion techniques. Next, we'll look at attack datasets for data execution and noise padding. The same set of control logic used in the traditional attacks is transferred to the PLC. However, this is not done in the same manner. This is done in the 2 attack manners as described earlier. These 2 attacks, for a reminder, are data execution and noise padding. So, these evaluation results can be seen in the table to the right. The packets of the traditional attack targeting the Modicon is detected on both signatures and DPI with a 100% true positive rate and a 0% false positive rate, whereas with the Micrologics, the traditional attack is detected on DPI with 96.78% of detection rate and 0% of false alarm. This illustrates that the network intrusion detection systems are working quite well against traditional non-evading attacks. Data execution nor fragmentation and noise padding attacks on the Modicon were detected a single time. As for the Micrologics, only the noise padding was able to be tested, and even up against the anagram-based deep packet inspection, 0 detections occurred. You might notice a huge increase in packets, and this is due to control logics requiring serious fragmentation down to 1 to 2 bytes. So as can be seen from this, it is shocking to go from almost 100% detection on Micrologics and 100% on Modicon to 0% on both. So now that we have discussed some alarming data, let's look at some of the proposed countermeasures. First up, we have user authentication. It isn't widely supported, and even when it is hardly seen in the field. However, further research would need to be done because even though it could prevent against these attacks, by verifying downloads, it is possible these authentications could have vulnerabilities themselves and hence be bypassed. Next, we have data execution prevention. This is very effective at protecting against unauthorized zones of execution, and is widely used in desktop and server environments. It is proposed that although the memory management unit that is needed to utilize such protections in those environments could be substituted for a memory protection unit found within available microcontrollers. Continuing right along, We have control flow integrity, or CFI. This seems like a great solution as it actively monitors the control flow and detects any type of change of plans. The real drawback is the overhead that would come along with such a solution. If a general purpose CFI solution is integrated, so in this case a customized PLC solution would need to be designed to avoid a hindrance in performance of real-time monitoring. Lastly, we have a robust network intrusion detection systems. All the solutions require rigorous studies, updates, and redesign of PLC, which is far-fetched to think it would be available anytime soon. A more readily available solution would be to invest research into revolutionizing the existing solutions. As an example, the authors suggested negating fragmentation and padding attacks by designing a network intrusion detection system to constantly use a mirrored space. In this case, it could catch anomalies based off the current and mirrored space as a mismatch. So in conclusion, both attack approaches are successful. Innovative solutions are going to be vital in the future, and more research is going to be needed to properly protect ICSs. So with that, here's a list of the references from the paper. And that concludes my presentation. I want to thank you all for joining me in this journey to discuss a first of its kind explorative paper into control logic injection attacks on industrial control systems. I appreciate your time and attention, and I look forward to any questions you all may have.